Okay, so in the second assignment, we have some length oriented in space AB moving to from position 1 to position 2. And we are supposed to design a 4-bar mechanism to move the length from position 1 to position 2 and give a complex rocker motion with no quick return. You attach a dyad to the motion to position 1 and 2 and make the linkage a 4-bar mechanism. You may also use, okay, that's not really important. Then we check for Grashof, we build a cardboard model, we determine the transmission angle at position 1 and position 2. So let's quickly get into it. Now, I should transfer these orientations onto my screen. Now, since I'm using this sheet, I don't have to use these dimensions to transfer them. All I need to do is to push this on the sheet like this. Use the compass to locate the point. So point A1 here, B1 here, A2 here, B2 here. And you come. So we have this and this. Okay. So we have A1, B1, A2, B2. You are supposed to design a rocker output. So just as we did for assignment 1, you join A1 to A2 with short dashes. You join B1 to B2 with short dashes. Then you bisect A1, A2. Then draw a line, you draw the bisector, and then bisect B1, B2, draw the bisector. Where they meet, let's label there, say O4. Alright. So the next thing is to attach the driving dyad. So to attach the driving dyad, I choose any point on the link, say this point here, and then I locate at the second position. So I use my compass. Okay, I want the dyad to touch the output link here, and I use the compass to check for the other position. So this is the link 1. So I would say, let's say here is E1, then here will be E2. Then I join E1 to E2 with short dashes. E1 to E2 with short dashes. Alright, so I should bisect this line and this line, just as I did for assignment 1. But this is already a bisector of A1, A2, which bisect E2, A1. So all you need to do is to use your compass, take half of the length and keep it. Make sure it doesn't change. Then you extend this line to any length of your choice with the length you took as the radius. You stand at that point and you draw a circle. So let's verify that. Great. So you will extend the line to touch the other side of the circle. So when we are at E2, our coupler will end at F2. When we are at E1, our coupler will end at F1. The center here, let's label it O6. We are done. So the next is to check for Grashof, build a cardboard model, and determine the transmission angle. Okay, so let's quickly get into it. So the Grashof will use this the driving part of the mechanism, which is O6F FE E04 0406. So for Grashof, we say the shortest plus the longest should be less or equal to P plus Q, the other side. So I will choose, not like I will choose. So the Grashof will involve the O6F. So O6F1, O6F2 is the same. So O6F is equal to, so take that measurement. That is 1.6. Then FE, so F2E2 or F1E1, that is 11. Then EU4, that's a 3.2. And then 0406, 11.5. Alright, so what is the least? 1.6. What is the highest? 11.5. We are saying this should be less or equal to 11 plus 3.2. So this one will give us 13.1, which should be less or equal to 14.2. So this means the Grashof condition is satisfied or is ensured. So the next is to check for the transmission angle. The transmission angle is the minimum angle the coupler makes with the output link. So these two angles, alpha, beta, the list there. So use the protractor, you put it here. Okay, so you measure the angle here, and we have theta to be 63 degrees. So the transmission angle at position 1 is 63 degrees. Then we come to position 2. There too, we measure, so here this is the biggest, this is the smallest. So you measure the one at the bottom. So put the protractor there. We have 61. So transmission angle at position 1 is, so we put something here. Transmission angle, we say is the minimum angle made with the coupler and then output link. So at position 1 we have 63 degrees. Theta at position 2 we have 61 degrees. So that's that.